Welcome students, and in this video we are going to wrap up the concept of method of characteristics. And to do that we are going to start with a problem, yes, and which is a very simple problem, yes, and we will build on that problem. So essentially let's look at this equation ut plus a constant. Let's consider the constant as a times ux equals to 0, and u at the point x0 is going to be some function phi of x. So phi is given to you, clear? Okay, and the point is this: we have already so let's call this as 1, call the second equation as 2. Now we have already known that you can actually solve 1. So solving 1, if you solve 1, then you get u of xy is a function, some function, arbitrary function f of x minus at, right? F of x minus at. And what is f? F is a c infinity function, yes. So this we already know from our previous methods which we have already learned, right? Okay, now you see the thing is this: if we want u of x0 equals to phi of x given to us, right? So phi of x has to be equals to u of x0, and from our equation, the first solving one, you have this which is f of x. So basically phi of x is equals to f of x, so we can actually assume phi to be equals to f. So therefore, okay, the solution which you are basically looking at should look like this: u of xy is equals to phi of x minus at, right? That is what it should look like. Okay, so now see this solution, yeah, this is our true solution, because this solution satisfies 1 as well as it satisfies 2. Okay, so now the thing is this: see, but let's say we want to make it more precise, right? How to solve this thing precisely? Let's just see that. See, what's happening here is this. So geometrically, again, let's look at the idea. This we already talked about in the first video of this week, right? But still, again, let's do it. So in this context, in the context of initial data, what we are doing is this. So first of all, let's say you have this. So geometrically, geometrically, what we are doing, geometrically, see, the thing is this: we have this gamma, yeah, that's your curve, and the curve is given by, let's say, x comma 0. Okay, so and x is in R, clear? Yes, and let's say this is be a curve in R2, curve in R2, yes, and this is the curve on which the data is prescribed, and the data is prescribed, the data is prescribed. Okay, so you see, if you look at the what is given here, you see on the line x0, so basically y equals to 0. So on x-axis the initial data is given. What is the initial data given? That the u on the x-axis, u at the point x0 is nothing but phi of x. That's the data given to us, right? So now the point is this: see, the solution which we want to construct, okay, we want that solution. So you see the solution, that will be if you look at the graph of the solution, that is going to be, so basically this is your, so think of it like this. See, let's say this is our this xy, x and y, and the graph of this particular u will be somewhere here. So basically it will be in 3 dimension. Okay, the graph will be in 3 dimension. Yes, so you see, when you restrict this particular graph to only x equals to 0, so basically this x-axis, then that will give you some curve, right? That will give you some curve. Yes, and that is your initial curve. So basically if you look at any one of the coordinates of this, so any point on that curve, how does the curve looks like? So basically the point will be x and 0 corresponding to x0. So let's say x0 and 0, and the height will be, so here it is given by phi of x. So basically the height is phi of x0. Okay, so what is the coordinate? There will be x0, 0 and phi of x0. So that will be the coordinate here. So you see the curve gamma phi, yeah, that will be the curve, is the curve in R3, and that will be given by this, given by x0 and phi of x. x0 phi of x, clear? And this curve lies on the surface. So this lies on the characteristic surface. So basically the surface which you are interested in. So on the graph of S, graph of U, our solution. Clear? That should be the case, right? Okay. So now you see what we want to do is we are going to find out the characteristic curves. So let's say at this point, yes, we will find out a characteristic curve which starts from this point and it goes on like this. You understand? And if we can do this for all such points on the characteristic curve like this, yeah. So basically, sorry, on the initial data like this, data curve, then you will actually end up getting a full, that surface. That's the idea. Okay. So how do you get it? Okay. So you see, we will construct the, characteristic curve. So these are characteristic curves, right? This is your initial data. See, there are two curves here. One curve is this initial curve, and another curve is those characteristic curves which starts from this initial curve. So the point of the characteristic curves are, so essentially, see, we want to construct. So the idea is to construct the characteristic curves. Okay, starting from let's say x0, 0 and phi of x0. Is it okay? Starts from there and it moves on. Okay, so essentially what are we looking at? What is the characteristic equation? The characteristic curve solves this equation, right? Dx by dt in our case is nothing but a. Okay, and what is dt by this is dx by ds. Okay, and dt by ds, this is nothing but 1, and then dz by ds is nothing but 1. 0, 0. Okay, and what is the data given, and what is x at the point 0? So x is a function of s here. Okay, see, this thing, this is parameterized by x and that is parameterized by s. So characteristic curves. Okay, so essentially this is a function of s, this is a function of s, and this is a function of s. Okay, so when s equals to 0, that is when x0, that will be your x0. Okay, and what is y at the point 0? So that, t at the point 0. What is t at the point 0? That is nothing but it is x0, 0 and phi of x0, right? So it is 0. The initial data, initial point is this, right? And what is z at the point 0? That will be nothing but phi of x0. Clear? Okay. So now you see, once you solve this, so basically if we want to put everything algebraically, what is happening here? Let's just write it like this. So algebraically, okay, okay, see, let's parameterize. So this is how I want you to solve this problem. Parameterize our curve gamma. So that's your initial data by r. So where I was writing this x, that will be your r. So our initial data is r0 phi of r. Okay, right? So and basically gamma should be written as r0. So that's your initial curve, initial data where it is given. And for each r, okay, we need to solve this. We need to solve the system to solve the following system. Okay, so what is the system? The characteristic equations. System. So you see, for a fixed r means, you see, I am fixing a x0, so that I am writing as r. So for a fixed r, I am looking for a characteristic equation. So basically characteristic curve, which starts from there. Okay, so what is the equation? It is dx by ds. You see, the characteristic curves are parameterized using s. Okay, so dx by ds is a function of r and s. Yeah, R and S, why? See, for a fixed R, yeah, when you fix R, so in this case R is, let's say x naught is fixed, so this point is fixed, x naught 0, phi of x naught, and then I'm looking for a characteristic curve which starts from there. So initially the initial point of starting is x naught 0, phi of x naught, and then it moves on according to this law, right? So this we wanted to write it properly. See, for a fixed R, this is a function of S, so dx by ds at the point S is nothing but a, and similarly dt by ds as a function of R of S is going to be 1, and then similarly dz by ds function of R of S is going to be 0. What is the initial data? The initial data is x at the point R0 equals to R, t at the point R0 equals to 0, z at the point R0 equals to phi of R. Clear? Okay. Now, if you solve these equations, so solving, what do you get? Solving, you get x of Rs is equals to As plus C1 of R. Okay. T of Rs, this you are going to get S plus C2 of R. So C1, C2, these are all constants. And Z of Rs, you are going to get just a constant C3 of R. Okay. Why I am writing this R? Because for a fixed R, I am going this. I am to get one constant. So basically, when R varies, the constant will be a function of R. Okay. So now we have the initial data. So if you put the initial data, now these things plus the initial data implies that x of Rs is nothing but As plus R, y of Rs is nothing but S, and z of Rs is nothing but phi of R. Okay. Now, if you replace all of this, definitely you are going to get that u of xt is nothing but your z, right? That is z of Rxt and Sxt, right? Which is nothing but function of x minus a t. Okay. Fine. So this is how you solve it, right? Now the point is this. See, here the initial data is given on the x-axis, right? And then we can solve it. What happens if the initial data is not given on the x-axis and in some other point? So essentially, we will look at something called a non-characteristic boundary data. Okay, boundary data. Okay, so what is the meaning of non-characteristic boundary data? Essentially, what happens is this. See, you have this equation again, ut plus aux equals to 0, and u restricted to some gamma is equals to phi. So what is gamma? Gamma is the curve in xt, where gamma is the curve in xt plane. Okay, xt plane. Okay, so initially, what is the gamma? Gamma is our x, the x-axis. That was our curve y equals to 0, and here I am restricting it to I'm not that x-axis, but any arbitrary curve which is gamma. Okay, that's the arbitrary curve. Now, so this problem is called the Cauchy problem. This is called Cauchy problem. Okay, so now you see, the thing is this: we want to find out under what circumstances can there be solutions, and if there is a solution, whether the solution is well posed or not. So we have already talked about well posedness. Well posedness means if there is a solution, is it unique? Okay, right. Now you see, so let's say that you consider okay, gamma to be this set of all x comma t such that x minus at equals to 0. Let's just consider this gamma. Okay, so you remember, again, let's call this as 1, call this as 2. Okay, so solution of 1 we already know it is a function of arbitrary function of x minus at, right? You remember? See, It's an arbitrary function of x minus 80. Okay, so here also if you solve, so basically now let's say that I give you this data that u restricted to this gamma, this is the gamma, is phi. That's the data given to us. So if that is the data given to us, then what is the solution? U of xt is an arbitrary function of x minus 80, right? And the thing is this, here you see, if you put this is just by solving one, right? Now if you want to solve the second part, you see u restricted to gamma is basically 0, right? So see, u restricted to gamma is basically phi, right? And u restricted to gamma is nothing but phi. Okay, so you do realize that, you see, gamma will be parameterized by r and phi, a of r. So therefore gamma can be parameterized by r and ar, right? Of course r is in r, huh? So you write it like this, sorry, once again, r is in r. So we can parameterize it like this. Now the thing is this, with the boundary condition we are claiming that this problem is ill posed. It's not well posed, huh? So with this data, the problem is ill posed. Why? Let's just understand this. Post. Okay, see, the thing is this, the functions, so the solutions which you get, they has to be constant along the characteristic. That's what are the characteristics of this equation? It is given by x minus 80 equals to constant, right? Yes. So equation 1, the characteristics of the equation 1 is x minus 80 equals to constant. Those are the characteristic lines, right? So you see, but the initial data is also a characteristic line. Okay, so you see, the characteristics of this equation, characteristics of one are given by x minus 80 equals to constant, right? And incidentally the data is also given along on one of the characteristic, and the data, you see, the data gamma, so curve, basically data curve is one of the characteristics, right? So what happens then what happens is, in this case, phi has to be constant along x minus 80 equals to 0. That will imply phi has to be constant along gamma, right? That is what it is saying, because you see, along the characteristic u is basically constant. On the characteristic curves u is basically constant, right? So if that is the case, then since the data is given, so data phi is given along one of the characteristics, so basically u has to be constant along that characteristic. Yes, so phi has to be constant, right? So but it may not be the case, right? So phi can be a function, right? It may not be constant. So you do realize that this actually creates a contradiction. So it should not be the only function which satisfies this equation, right? So what happens is, this is a case where the problem is not well posed. Yeah. Okay. So what's happening here? How do we put this information together? So we define something called a non-characteristic. So we say that gamma is a non-characteristic. So let me write it like this, is a non-characteristic. This is a shortcut, non-characteristic. So the gamma is what? Gamma is your data curve, right? So that is a non-characteristic for the Cauchy problem. Which is the Cauchy problem? It is given by a of xy, u of x plus b of xy, u of y equals to c of xy and u restricted to gamma is equals to phi. Yes, so that's your Cauchy problem. And the data curve, this gamma, so gamma is the data curve. Okay, so basically the curve along which we are given the data. Now you see that gamma, we will call it a non-characteristic. Non-characteristic, so it is called non-characteristics. Okay, gamma. The data curve is called. If gamma is nowhere tangent to the projected characteristics. Okay, tangent to the projected characteristics. And what are the so basically in this case it is A of gamma 1 of R, gamma 2 of R times B of gamma 1 of R, gamma 2 of R. Okay, so what does that mean? It means that this particular term, so this term, okay, times minus gamma 2 prime of R, gamma 1 prime of R, this has to be non-zero. So basically gamma, what is the the parametration of gamma? The parametration of gamma is gamma 1 and gamma 2. So this is parametration. So basically gamma is parameterized as gamma 1, gamma 2 of R, gamma 1 of R, gamma 2 of R, right? So essentially if you look at, if this is the gamma, this is gamma, any point is given as gamma 1 of R, gamma 2 of R. Okay, so if you look at the tangent to that point, so basically that will be gamma 1 prime. So this is the tangent, right? It will be gamma 1 prime of R, gamma 2 prime of R, and then the normal with to that is given by minus, this is your normal. So essentially what this is saying is this, the projected characteristics, which is this. So basically this is the projected characteristics. So this projected characteristic should not be, so that gamma should not be nowhere tangent to this projected characteristic. So basically this times the normal, that should not be 0, because if they are 0, if these two product is going to be 0, it means that they are perpendicular to each other. So basically it means that these two, the gamma is actually tangent to the projected characteristics. Okay.